So I'm Tom, that guy over there, and I'm a PhD student at the University of Leuven. And this means that I play with things. I try to find things that are interesting. And well, personally, I'm very interested in web security, so I play a lot with things in the browser. And one day, I encountered something that I couldn't explain. So I saw that when I sent a request that had a response of 10 kilobytes, the request took around 10 milliseconds to complete. But when this response grew to 15 kilobytes, suddenly the time that was needed to download the resource doubled. And yeah, this doesn't really seem logical because, well, it should be, I thought that it would grow linearly. So I have a lot of colleagues at the university. Some of them are here. So I went to one of my colleagues called Matti, and I told him about this, and I asked if he knew what could be the cause of this. And well, apparently he had some idea that it had to do with TCP-windows. So then I went to look into what TCP-windows are, and then I figured out that actually the things that I couldn't describe at first could actually be used as part of an attack. Brief demonstration and talk about the countermeasures that could be used to defend against this. But let's start with the same origin policy. Can you see what's on the screen here? Yeah, well, if not, look at that screen. We have a website on the right-hand side, so bunnybang.com. And on the left-hand side, we have Mr. Sniffles, who is a customer of bunnybang.com. And in some previous time, he had logged into bunnybang.com, so he has some cookies that are sent along to requests to bunnybang.com. So when Mr. Sniffles wants to look at the contents of his vault, he sends a GET request to the vault endpoint, and bunnybang.com will reply with a resource with the contents of the Mr. Sniffles vault. But of course, bunnybang.com is not the only website there is. when we go on the web, we go on the World Wide Web. So there's, Mr. Sniffles also looks at funny rabbit videos, Instagram pictures, some maybe naughty websites. And from time to time, he also ends up on some creepy, malicious website. And all these websites, they can do things with the browser of Mr. Sniffles by, for instance, returning some JavaScript code. And well, this JavaScript code can do quite some things, but for the purpose of this attack that I will be presenting later, the thing to keep in mind is that it can also, trigger requests to any other website, including bunnybang.com. So the browser of Mr. Sniffles can trigger requests to bunnybang.com to any endpoint, just by having JavaScript run on a different website. Now, of course, bunnybang.com does not know from where this request originated, so it will return the same thing as before. So it will return the contents of the vault. But of course, as I said, there are some malicious players outside there on the World Wide Web. Let's look at this guy. So in our attack model, we assume that this guy is a man in the middle. So a man in the middle means that he can intercept or, look at the network traffic that is sent between Mr. Sniffles and Bunnybang. Of course, bunnybang.com is a secure website, so it's loaded over HTTPS. So it's actually not possible for the bad guy to look at the contents of the vault, but because SSL or TLS has no padding that tries to hide the length of the resource, what the bad guy can do is look at whether the vault is large or whether it's small. So you can look at the size of the vault. So that brings me to the second part of the technical background, compression-based attacks. And before I can go into attacks on compression, I first need to explain how compression works. So on the left, we see the uncompressed version of a resource. So this part is the actual resource that's being sent. So uncompressed, if you count the number of bytes there, you come to 51 bytes. And when we compress it with gzip compression, for instance, we see that the string vault occurs twice. So it's easy to compress this by, in the second occurrence of vault, we have a back reference to the first occurrence. So at this point, it just states, you can just point to, you go back this many characters and you will encounter the same string. And that allows you to compress the resource a little bit. So you can see that uncompressed is 51 bytes, and by compressing it, it becomes 47 bytes. So now to the attack. How can this mechanism be abused by an attacker? So the attacker is the one that is sending the request, so he can choose which request he sends it to. So we have now some reflected content. So the requested URL is reflected in the response. So you can see you requested and then the complete URI that was requested. Now in the first, so the left-hand side one, you see that the vault is back referenced as before, and then there's the string secret and equals. So that can be back referenced to the one that's stated before. But because the A is different from the character C, it cannot back reference that additional character. while if the attacker would guess the character C here, the character C would be would be part of this back reference as well. So this means that it's 1 byte smaller than when the character A is guessed. So is this kind of clear to everyone? If it's not, then so that's basically the idea behind compression-based attacks. And this allows the attacker to guess the character guess the secret byte by byte. So again, then he guesses A, and he sees that the size of the resource is 49 bytes. So that means that the compression worked better because there was a longer sequence that could be back-referenced. And with the character B, that's not the case, so it's 50 bytes. And basically you can do that to get the complete secret. So these are, well, these kind of attacks have existed for quite some time already. The first occurrence that I found was from some academic conference held in 2002. And they basically said that when we have a chosen plain text and that with some secret information and that resource is compressed, then we can leak information about the plain text. And then it was, let's say, rediscovered or applied to SSL with crime, and then later on again with breach. So crime was on SSL compression, so the compression in SSL itself, and breach on HTTP compression, so with gzip compression. And then, yeah, there were some others like time that uses timing information and so on. So that brings me to the third and last part of the background. Okay, so everyone said that they knew TCP, so well, this also doesn't really matter, but, well, so when you make a first connection with the bunny bank, Mr. Sniffles will need to do the TCP handshake and then the SSL or TLS handshake. And after that, it will send the GET request. So it will encrypt the GET request, so with the, well, the URL and then the cookie, the host, and all that. And then it will use TCP to send it over to Bunnybank. And because the GET request is relatively small, it fits in a single TCP data packet usually. But so when the bunnybank.com sends back the vault to Mr. Sniffles, he first, of course, encrypts the vault. And because Mr. Sniffles is a rich guy, the vault is relatively large, so it doesn't fit in a single TCP packet, but it needs to be split up in 29 different TCP packets. So one TCP packet is around 1.4 kilobytes, I think. That could be wrong, but yeah. But so TCP works with congestion windows. So this means that bunnybank.com can only send a number of TCP packets without having an acknowledgement of Mr. Sniffles. So typically the initial congestion window is set to 10. So bunnybank.com can send 10 TCP packets to Mr. Sniffles before it gets an acknowledgement of Mr. Sniffles. So when all these 10 packets have arrived, Mr. Sniffles can start acknowledging them. So he sends 10 acknowledgements. And then for every TCP packet that was acknowledged, the congestion window grows by 1. So then the congestion window becomes 20. So now Bunnybank can send 20 TCP packets without them having, well, them being acknowledged. But since it's already sent 10, it only needs to send 19 more. So it just sends everything to Mr. Bunnybank, to Mr. Sniffles. Yeah, so does everyone understand how this works? Because that's I think the most important part. So it basically is that you can't send all data at once, but depending on the congestion window, you need to wait until it gets acknowledged. So that's an additional round trip that is required. Okay, so that brings me to the actual content. Heist is a set of techniques that allow an attacker to determine the exact size of a network response. And the cool thing about it is that it can all be done purely in the browser. So you don't need a man-in-the-middle attacker, but just by visiting a website, an attacker can determine the exact size of a response. And this can then be used to launch compression-based attacks, such as crime and breach, purely in the browser. And in order to do this, we exploit certain side channels which are related to timing. So first, the first side channel is that we want to discover when the first byte of a response has been returned by bunnybank.com. So we use the fetch API, which is a relatively new browser API related to, well, it's kind of taking over the XHR thing, and it allows you to send requests to any URL. And it, well, returns a promise, which is also something relatively new in JavaScript, but it really doesn't matter. It's just that it resolves, so some kind of callback is executed as soon as it resolves. So you, as an attacker, writing this JavaScript, you can know when the first byte of the response has been received, because then some of your code will be executed, and you can look at the current time then. And you can also look at when the resource has been completely downloaded. And you can do that with the performance API. You can look at the last entry and look at the response and attribute. So with Heist, we want to determine the exact size of a response. And the first step to do this is to figure out whether the response fits into a single TCP window or not. So let's look at the timeline. So first we have our fetch, which is triggered by the attacker. This will initiate a TCP handshake to the IP address of bunnybank.com. And then it will do the SSL handshake as well. It will send a GET request, and then once the bunnybank.com receives this request, it will return the response. So that's the initial TCP window sent. And then at what I call T1 is when the first byte of the response has been received by Mr. Sniffles. And well, that coincides with the resolution of the promise that was returned by the fetch operation. And then really moments after, because when multiple TCP packets are sent at once, they will, the timing difference between the arrival of the first one and the last one will be a matter of milliseconds. Like 1 or 2 milliseconds, maybe, depending on the network. And then because the resource fits in a single TCP window, the difference between T1 and T2 will be very small, because only a single not an additional round trip is required. Now, when the resource does not fit into a single TCP window, the first part still looks the same, except where there was T2, there's now the initial TCP window received, but not the complete response has been received yet. So at that point, Mr. Sniffles will send acknowledgements, well, TCP-X, to Bunnybank. And upon receiving these acknowledgements, Bunnybank will send the second TCP window. And when Mr. Sniffles received this second TCP window containing all the rest of the response, this will be T2. So if you compare with this one, the difference between T1 and T2 is very small, whereas this one, there's a complete round trip between Mr. Sniffles and Bunnybank. That's between T1 and T2 here. So it's, well, very easy for the attacker to determine whether it was in a single TCP window or not. But of course, this only allows you to determine whether the resource was smaller than 15 kilobytes, so one TCP window, or larger than that. And it doesn't really give you information about the exact size of the response. So for that, we will need another trick. And we will use something like this. So the colors are not very clear. So look at on that screen. So the green part is the resource that we want to know the size of. At this point, we assume that it's smaller than a single TCP window. So there's this green resource that we don't know the size of, but we can reflect some content. So as we saw before, with you requested this URL, and because, well, the content is determined by the attacker, he can choose exactly how many bytes that are used there. So that's a part that is known. So then he tries to determine whether the complete response, so the green part and the orange part, fit into a single TCP window. He notices that it doesn't, so then he reduces his X bytes, so he divides them by 2. And then, well, he does the same thing again, so then he checks, does it fit in a single TCP window? Then the answer is yes. So then he again needs to increase the number of reflected content. He increases it by a fourth of X. And well, this goes on and on until, well, after log n checks, he finds a certain amount of bytes, y in this case, and if he reflects this amount of bytes, he discovers that it fits in a single TCP window, and when he adds one more byte, he finds that there are 2 TCP windows that are required to send the content. So then he can easily subtract the y bytes from the initial congestion window, and that gives him the resource size. So let's refer to this as the tipping point, because, well, for y it's 1 TCP window, and y plus 1 it's 2 TCP windows. Okay, so that's cool already. So you can determine the exact size, but only for very small resources. Of course, it wouldn't be cool if we only could do that. Well, it would be cool to some extent, but not cool enough. So let's look how we would do it for larger responses. And there, the attacker would use a trick to first increase the congestion window to a value that he wants. Because TCP works in a deterministic manner, it's easy for him to increase this TCP window. So first, the TCP the initial congestion window is set to 10 TCP packets, which is around 14 kilobytes. And when packets are acknowledged, the TCP window grows. So the attacker can arbitrarily increase the window size. And he does this as follows. So in this case, the vault is 19 TCP packets large. So first, the attacker sends a request to foo, which is a completely unrelated resource, which happens to be 10 TCP packets large. So, well, the initial congestion window here is 10, so the foo resource can be sent at once. And then upon receiving these TCP packets, Mr. Sniffles will acknowledge them. And when those acknowledgements have been received by Bunnybank, the congestion windows grows to 20. Because for every acknowledgement, it grows by 1, and 10 plus 10 is 20, of course. And around the same time, Mr. Sniffles sends the request to Vault over the same TCP connection. And because the congestion window is 20, and the Vault is only 19 TCP packets, it can be sent in a single TCP window. And well, basically this allows the attacker to perform the same attack as we saw with a single TCP window, but now with a larger TCP window. Okay, and of course, for all this, the attacker, so in step 2, we saw that the attacker requires some reflected content, so some content from the request that is reflected into the response. But unfortunately for the attacker, this is not always available. So the attacker wants to maybe use something else. And in the, I think, last step, I'll show how we can leverage HTTP2, which is the new HTTP version, to achieve the same thing without having reflected content. So HTTP2 is the new HTTP version. Who has heard of it? Okay, many people. So it works very similarly to HTTP. The main difference is on the network level. So now when I would send 3 requests at the same time, my browser would open 3 TCP connections to get those 3 resources. But with HTTP, only a single TCP connection is used for parallel requests. So that's quite interesting. So yeah, by leveraging HTTP2, the attacker can determine the exact response size without having reflected content. And for that, he will leverage content from other resources that are located on the same server, so that can be accessed over the same TCP connection. And well, if you would like to use a compression-based attack, such as breach, you still need to have some parts of reflected content. Otherwise, you can determine what gets compressed or not, but for that you only need a few bytes of reflected content and not several kilobytes to determine the exact size. So let's look at an example. So in this example, the vault of Mr. Sniffles is 6 TCP packets, and a request to another resource is 4 TCP packets. So so we want to figure out, so the attacker knows exactly how many TCP packets is the second request, so the actual first request, so the reflect one. So he knows that there are 4 TCP packets in this response to this request. but he doesn't know how many there are in this one. So he wants to figure out, does it fit in a single congestion window or not? And so he sends a request to both the reflect and the vault at around the same time. This sets up a single TCP connection, and it will, well, Bunnybank will return 10 TCP packets because the vault, that will be the contents of the vault plus this reflect resource. So 6 plus 4 is 10 TCP packets, which fit in a single congestion window. And as you can see, the difference between T1 and T2 is very small, so the attacker knows this fits in a single TCP window. Now, when he grows the size of the reflect, so it becomes 5 TCP packets, then he notices, well, now I now the difference between T1 and T2 is larger because 2 TCP windows were required to send a response. And basically that allows attackers to open the vaults and perform their heist. So that brings me to a demonstration. Yeah, I'll wait until it's up there. So you see, here there's the Bunnybank website where bunnies go for doing their transactions. So here we log in as Mr. Sniffles. Unfortunately, Mr. Sniffles is not that rich anymore. And well, on the website you can perform transactions, but of course the website is quite secure. So they prevent cross-site attacks by having a CSRF token here. Yeah. So as you can see, there's an input type hidden with the CSRF token with a unguessable value. So in our attack, in this demonstration, we will try to determine the value of this CSRF token. And if the attacker manages to discover it, he can make Mr. Sniffles send arbitrary amounts of carrots to a different bank account. So we close bunnybank.com. But we are still logged in there. Mr. Sniffles is. And then, Mr. Sniffles goes about his daily business and goes on the New York Times website. There's some cool video there. So, I'm just starting to play the video to show that even if there is background traffic going on, it doesn't really affect the attack. This is also for demo purposes. So normally all this would be happening in the background and Mr. Sniffles would have absolutely no clue that this was happening. So in the first part of the attack, we need to determine this tipping point, so the value y, where y is if y plus 1 needs 2 TCP windows and y only needs a single one. So here you can see the timing. So we found that the tipping point is 14350 bytes. No, 14,349 bytes. And so here we have first some invalid guesses, and well, that's why we have 1 byte more than the actual tipping point. And you can see that the response time here is much larger than, so here it's normally, well, if the difference between T2 and T1 is like 2 to 5 milliseconds, it means that it fit in a single TCP window, and in this case, it's around 20 milliseconds, so that's 1 additional round trip that was required. And yeah, basically then the attack goes on and it guesses the first value. Yeah, I should also mention that this is, I think, in lifetime. So the attack, well, it just managed to discover the second character. So it only takes a few seconds to do this. And this is also in a, well, I would say unoptimized manner that this is performed. So it can be parallelized and made much faster than this actually.
Can you still parallelize it with HTTP2? Because it will send the requests in parallel. If you parallelize it, then it doesn't work.
Yeah, then it indeed won't work. And it could be that if you abuse subdomains, then it might work. I'm not entirely sure. I think it will finish very shortly. Yeah, so you see that, well, the value that was found was exactly the same as the one as on the website that we showed. So yeah, the attack works. So I would say that this is a pretty bad attack because it can be launched against many targets. So you can launch a compression-based attack. So that's what we just shown in the demonstration by abusing gzip compression. And since gzip compression is, or compression in general, is used by virtually every website to save on bandwidth, it was actually hard to find websites that are not vulnerable. But in addition to this, there's also things like size exposing attacks, which are more related to the privacy of the user. So you can reveal the victim's demographics from popular social networks. So if you can determine the size of a certain response, you can figure out the age of someone if they are logged into Facebook, or their gender, or their location, or basically all kinds of details that Facebook has, but not some random websites that you don't know about. Well, they should definitely not have them. Yeah, and if you would be logged into medical websites, such as WebMD, which is in America a quite popular one, you can also launch attacks against them and reveal health information about victims. So the attack actually covers quite some areas. So there's the browser-based things. So the same origin policy on one hand, and on the other hand, there's also the timing side channels that are being abused there. And then on the HTTP layer, well, obviously the compression is used there. Um, and then on the network layer, there's the TCP windows that are being abused. So on each of these layers, you could look for defenses. And well, we've listed 6 here. I bet that there are plenty of other possible defenses. Unfortunately, not all of them are good defenses. So you could try to close the side channel leaks. But since browsers are such complex things, it's very likely that if you close one side channel leak, there might be 20 others that you don't know about, and these could still be exploited. I think basically the only good solution, in my opinion, is to disable third-party cookies. So the whole attack works because if I go to evilsite.com, this site can trigger requests to bunnybank.com, and my cookies that I have with bunnybank.com are sent along to this request. And I personally, this has grown because of the whole evolvement of the web, but I definitely would like this to be prevented. So there's some new browser called Brave, which does this by default, which I personally think is a very good initiative. Then on the HTTP layer, you could try to block illicit requests, but then again, there are tricks for the attacker to make the requests look legitimate. So that's also not a very good solution. Disabling compression, that would solve the compression-based attack if the compression of secrets would be disabled. But unfortunately, the leaking of, the size of resources, so to get the demographics of the victim from Facebook, for instance, would still be possible. And then on the network layer, you could try to randomize the size of the TCP congestion window, but randomizing is never a very good approach to something, so I don't think that would actually work. And trying to apply random padding also might not really work, because again, if you have a lot of random values and you take the average, you still have you can still figure out the actual value. So that brings me to the conclusion. So I presented Heist, which is a collection of techniques that can be used to discover the exact size of a response purely in the browser for all kinds of authenticated cross-origin resources. Heist abuses some side channels which originate from the interplay, so the play between the TCP layer and the browser, and also some part of the HTTP layer. And by determining the exact size of a response, you can an attacker can exploit compression-based attacks and size-exposing attacks. And another thing that's quite interesting, I think, is that when HTTP2 is enabled, so basically the future, the exploitation of these attacks is made easier, and there are many possible countermeasures, but only very few that actually work. So, yeah, if you have any questions, I'd be happy to answer them.
Can you maybe go back to the overview slide with the timeline? This one. So this time 1 here, is basically a callback response?
Yeah, you could.
So at that point you need an accurate timer, right? Is that available in JavaScript for this purpose?
Yeah, so you need a timer that's around, that has a resolution of around 1 millisecond. The timer that's available in JavaScript has a resolution of 5 microseconds.
Okay.
Mm-hmm.
Why didn't they offer it?
B-
Would it be like one solution of solving this? Because your side channel critically relies on this response end as well as this promise. Well,
yeah.
omitting the promise is probably more difficult than omitting this response end API.
Yeah, so there are likely to be other side channels that could be exploited there because, well, it's the end of the response, so something is happening. So, yeah, even if they would not make this available, so I think it's made available because it offers some valuable information for developers or people that are running a large website and they want to determine the performance of their websites on their clients, with their clients. So that's why I think they make it available. But even if it wasn't, it's very likely that there is another other type of side channel that could be exploited to achieve the same, to return the same, or to run a function that is executed around the same time.
So you do something similar as the first time step, try to lead to some promise that fires or response end.
Yeah, actually I know of a different side channel that does this. So you could, what you can also do is, if you have, so this promise, so you have the fetch that returns a resource, and you can place this resource in the cache. So the service worker cache thing. So it's a programmable cache, so you can place it in, but when you then request it from the cache, that can only resolve when the resource has been put in completely. Then you know. So basically you try to put it in the cache, read it out, and when you read it out, then you know it has been downloaded completely.
I see. Thanks.
So with this stuff, you need reflection, right, to make this work?
So if you
Because you can't manipulate the size of the response when it comes back if you don't have reflection.
yeah, so that's why you can use HTTP2. Then you don't need reflection.
Why is that?
Wait. Because in HTTP2 everything is sent over a single TCP. Yeah, so this is the example with HTTP2. So here you send two requests. One is, I call it reflect here, but it could as well be a resource that you know the size of, or a resource that you upload, for instance. But yeah, you need to know the size of this one. So this is 4 TCP packets, and this one is 60 TCP packets. You send a request to both. That's over the same TCP connection, and then the response is also sent over the same TCP connection.
And the first actually kind of manipulates the length of the response, right?
Yeah, indeed.
Would you recommend people using a different browser just for their bank activities?
Maybe. I think it wouldn't hurt. I don't know if it would cover all the possible attacks.
Wouldn't that be equivalent to disabling third-party cookies in your browser? Like, it would be the same thing, more or less, if you use a separate browser completely, or if you just disable third-party cookies in the same browser that you use for other things.
Yeah.
Roughly.
Yeah, but the thing is that I'm not entirely sure if you, well, you can disable third-party cookies, but the way it's implemented in the browser, I'm not entirely sure if it's sufficient to prevent these attacks, but that's still part of some ongoing research, so I don't know the exact answer yet.
How do you target a specific part of the request? For example, in the demo, the CSRF token.
Mm-hmm.
So why doesn't it match on anything else in the request or the response?
Well, a CSRF token is by default very unique. Well, it needs to be, otherwise the attacker can just guess it. So because it's unique, the chances of it matching with something else in the response is, well, close to 0, I think. Because, well, you need a string of at least 3 or 4 bytes, so 3 or 4 consecutive bytes that can be back-referenced. Otherwise, there's nothing to, otherwise the compression would actually make the resource larger.
So if in the response something else is changing randomly, then it would be difficult. For example, a timestamp or...
That would be difficult if the length of this thing that's changing all the time. So if there's some dynamic content with exactly the same length all the time, so the timestamp, for instance, then it wouldn't really matter because, well, it's not part of the gzip compression. Wait. I lost my own train of thought. Yeah, but so if the content would change both in, would change in length, for instance, then it would make it harder for the attacker to discover the real size. But again, you can see it as some kind of random padding, and to tackle randomness is just to send multiple requests and take averages. So that's something that the attacker could do, but then of course it will take a bit longer for the attack to run.
You're doing this through the browser, but let's say you have like a root shell and you can TCP dump the incoming packets. Can you then, based on the packets you get, do the same attack?
Yeah, so that's basically what they did in the breach attack. So there, you can you don't need all this fancy side channels to determine whether it fits in a single TCP window or not, because SSL or TLS does not add padding. That means that you can, as an attacker, from inspecting the network traffic, you can immediately see the size of the.
What parts of the plain text can you actually expose this way? Because I assume you can only expose particular parts of the plain text, right? You cannot never actually decrypt the whole thing. I mean, is it specifically content or
theoretically speaking, you could, I think, discover everything on the page, but that would take a very long time to do. And yeah, so in the demo, it took around, I think, 1 minute or 2 minutes to have this string of 7 or 8 or 9, I don't remember exactly, bytes. So if you would do that for 20 kilobytes of response, that would take a very long time.
But once you had the token, couldn't you log in then as a person?
You can't log in because you don't know the cookie, but you can trigger, you can make a post request to this endpoint with the CSRF token, and then you can send money. Yes. So yeah. So there are, well, NoScript is, I like well, the idea behind NoScript, that you don't execute JavaScript. Unfortunately, it has been bypassed sometimes, so that's one point. And on the other hand, I don't know exactly if, well, it could be, but I'm not sure of it, that these attacks might also work without having JavaScript. So if you do some tricks with placing images at the right, well, right time, well, so images may be loaded sequentially, well, sequentially, I mean. So if you enter an image with a resource, well, pointing first at your own server, then the remote server, and then again your remote server. Sorry, so your own server, then an image pointing to the remote server, and then again an image to your own server. You can determine the difference in time between the first request to your own server and the second request to your own server, and then you get the timing of the second image. Is that more or less clear?
I'm just wondering how that executes, will execute the attack on your browser.
Sorry?
What does the timing of loading image have to do with executing JavaScript in your browsers when you visit an attack website? If you use NoScript by default,
Mm-hmm.
then if you visit an evil website, then the script that executes the attack doesn't load.
Uh-huh. But the attacker could make an evil website without, so he could try to launch these attacks without having JavaScript there. But because, well, NoScript doesn't prevent images to be loaded, so you can still measure the time of a certain request to an other website by also sending a request to your own website. So if images are loaded sequentially, and you first send a request to your own website, so you can record the time that this request was sent, then the second image points to the side of the target. So then the browser that doesn't run any JavaScript, but it does load images, loads this image. And then after that image has been downloaded, it triggers the request for the third image to your own website again. So then you can measure the time between the first request and the second request, and that should give some indication about how long the request to the target took. So then you can actually, then you have some kind of timing side channel without having JavaScript running in the browser.
To use that practically, the user would have to refresh its page all the time, and you would have to send different images of different sizes.
Well, you can also refresh your page without JavaScript.
Okay.
Any other questions?
I agree that the content of the token shouldn't change. Why is it
Yeah, so typically CSRF tokens do not change constantly, but they remain valid for a certain period.
Randomizing your congestion window has the same issue as randomizing your padding, that you can take an average and
Yeah.
And does this stuff still work if you use TCP fast stuff, for example?
Yeah, well, so I'm not that much of an expert in TCP. So the TCP thing is the one that I asked my colleague about. So I'm not entirely sure how TCP fast start works. But yeah, we can discuss maybe afterwards.
Is it being seen in the wild already? Did somebody already use it on a practical case?
Not that I know of. Okay, yeah, if there's no more questions, then, well, thanks for coming.